Welcome everybody. Today is lecture 20 of our lecture series on image processing. And as you can see from today's overview, it appears to be fun what we're going to do today, because finally we are going to study artistic image effects, which is in a certain sense, this is definitely has nothing to do with science. Right? This is just fun. The science in what we are going to do today is not so much the question why to compute artistic image effects, but rather how to do that. So it's an interesting computer scientific problem to actually do this. The reason why you would ever do this is hardly scientific. I just, out of the top of my head, cannot think about any serious application of that. But again, it is a lot of fun, and it's a problem in its own with respect to how we could do this. So what is this all about? If you remember last time, we began to discuss the following setting. Let us assume that we are given an image, let's call it a function g, defined over a set of two-dimensional coordinates, which on the left-hand side of this picture I refer to as coordinates u and v. So we have a function that is defined over a two-dimensional set of coordinates, so that for every coordinate we do have a certain, in this case, intensity value, since these are intensity images. Well, it could of course be color values, is not a big difference. It's just sort of, this is easier to discuss, right? That's all there is. And what we want to do is to apply transformations to the coordinates. That is, we are interested in functions t, transformation, that are being applied to the coordinates. So we do something with the coordinates, but not with the intensity values. For instance, if we were to rotate this point, uv, which I'm indicating by this cross here, by, I don't know, what is it, 10 degrees or something about this point, so there is a certain rotation here, it would end up here. Right? So we have transformed this coordinate, uv, into a new coordinate x, and we then create a new function, g tilde, which now I define to be defined over a two-dimensional set of coordinates, which I refer to as x and y. And this is just to distinguish between the coordinates in the original image and the coordinates in the new image. So if we apply transformations to these coordinates, we obtain new coordinates. But what we are interested in right now is the question, how can we create new images which are new in the sense that at a certain new coordinate, they assume the same intensity or color value as the original image at another coordinate. And this idea of basically doing something to the coordinates of intensity values, but not to the intensity values themselves, this is what we call warping. Image warping. So a warp function is a function that, given an original function g of u, does something with the coordinates u. So we have a transformation that is applied to the original coordinates. And this transformation applied to the coordinates produces a new image, just by setting the intensity values in the new image at certain coordinates x to the values they have in the original image at coordinates u. That is all there is to it. And we discussed possible approaches as to how to accomplish that. All right? And a naive idea could be to say that, okay, we are given an image. Let's think of this schematic representation on the left-hand side as a representation of the pixels of the original image. And let us apply a so-called push warp. That is, we would iterate over all the rows and columns, so that we would do something like this, in the original image. and apply a transformation t to the coordinates of the pixels in the original image, and thus obtain coordinates of pixels in the new image. And for instance, at this pixel, we would set the color value of this pixel in the original image, and at this pixel, we would set the color value of the pixel in the original image here. This obviously is sort of a reasonable idea in the sense that, okay, we are sure that for every pixel in the original image we are given, we actually do something. Right? It has, of course, the problem that by applying this approach, we are not guaranteed to do something for every pixel in the new image. There are certain pixels for which we do not compute an intensity value if we apply this idea. We sort of leapfrog over certain pixels in this new image. And here is an example as to what that may entail. On the left-hand side, we see the original image, and on the right-hand side, we see the new image, which, to our eyes, appears to be very dark. And that is because there are 3 columns in this image that are totally black. Then there is a 4th column that has the intensity values from this image. Then there are 3 additional columns, totally black. Then there's a 4th column that has the intensity values from here. To our eyes, it looks like that. Right? This what we see here is basically a perceptual artifact, because we see the stretched image, the warped image, and it appears to be very dark. And this is because, for practical reasons, for those I originally initialized all these pixel values to 0. And that is to say there would be like 3 columns here, like totally 0, then 1 column that would have the intensity values of this column, then 3 columns totally 0, then 1 column that would have the intensity values of this column, and so on and so forth. To our eyes, that will look like this. And this is certainly not what we do want to have, so what could we do? A smarter idea would be to sort of turn this process upside down, which is to say, instead of iterating over all the pixel coordinates in the image we are given, we could also iterate over all the pixel coordinates in the new image that we want to create. And for every coordinate in this image, for every pixel at a certain coordinate, we would apply the inverse transformation, the inverse function of what we're actually interested in doing. So instead of computing x from applying t to u, we consider a certain x and apply t inverse to get a certain u, and then read the corresponding intensity value from there. This has the additional advantage that the size of the new image can be chosen arbitrarily. Right? We can choose it to be of the same size as the original image, can be smaller, can be larger, doesn't matter, because if we iterate over all the pixels in this new image, we are guaranteed to be able to compute an intensity or color value for each pixel here. This is called pull warping, because sort of it pulls the intensity values from the original image into the new image. Here is how the result would look like in the case of this simple example of scaling by a factor of 4 along the x-axis, or the horizontal axis. This looks much better. This is sort of what we want to have. There is another technical difficulty we would have to address once we agree on that this is a good idea. Because even though for certain pixels, say this one, if I were to backtrace this arrow, I would end up here, we are guaranteed, maybe, depending on t, to to find a corresponding pixel in the other image, in the original image. But as you can see in this, again, schematic, metaphoric illustration here, this does not hold for every pixel in this image we want to create. Right? If we apply the inverse transformation for certain pixels, it may happen that it would lead us to a location in between two of the pixels, or more of the pixels in general, in the image that we are given. And again, like, images are digital, discrete structures. They have sort of a discrete grid of coordinates. And this transformation, depending on how we choose it, is not guaranteed if we compute the inverse to produce two integer numbers. It could be two real values. If we, this vector u will in general be a real valued vector, two-dimensional real valued vector, some numbers in between these discrete coordinates. And so we discussed the problem of interpolation. And last time we focused on the case of one-dimensional functions, of interpolating one-dimensional functions. That is, the setting we considered was that we are given a function f defined over just one parameter, and these parameters xi are supposed to be discrete sample points. That is, it's not a continuous function, but a discrete function. So we are given something like that. These black dots are located along the x-axis at certain sample points, which I'm referring to as points xi. And what we want to obtain is, given this discrete set of coordinates and corresponding function values, what we do want to obtain is a continuous representation, and I call this one f hat of x. It's not f of bracket xi, but f hat of parentheses x to indicate that this is supposed to be a smooth continuous function. Okay. In particular, we want to have something that allows us to compute the value of the function at a point in between x, some point in between two of the sample points. And here I am showing you, just for didactic purposes, what I did to create these figures. Actually, I turned again the process upside down. I was given the blue function, and then I sampled it at certain points. And sort of I created a discrete function by sampling a continuous function. The reason why I did this here is, next we'll look into how to interpolate this function, and by starting with a continuous function to obtain a discrete function and then to interpolate this discrete function again, this allows us to have a look at the quality of different kinds of interpolation techniques. So for the next couple of slides, we are talking about three different objects. We are talking about a continuous function f of x, which is, in our case, given for didactic purposes only. We are talking about a discrete function f in brackets of xi, and about the interpolation function f hat of x. Now, the first thing we looked into was the idea of nearest neighbor interpolation, and that is, we create a function f hat that looks like the orange one here. Right? Now, this is now definitely a function that allows us to compute a value at, I don't know, some coordinate x. Say at this point here, we would have this value. And it captures the gist of what is going on here. There's like no slight variations, and then they become larger. But if we compare this orange curve to the blue one, we see that, okay, it's definitely some interpolation, but it's not really very close to the original blue function. That's, well, not really desirable. But nevertheless, what could be an advantage of this idea? So why would I discuss something like this if at the same time I would diss its quality. I would say this is a poor interpolation. Why, if I say this is a poor interpolation, would I discuss it anyway? Yeah.
Maybe because it's faster.
It's extremely fast. This is extremely fast. If you want to compute this is instantaneous. So there are merits to this. There are merits to this. I am belittling it from the point of view of quality, but from the point of view of computation speed, you cannot be better than this. This is certainly the fastest interpolation technique we have. Another idea could be to say that in between any two sample points, we interpolate the function in terms of line segments. Now we see there are these orange line segments, as we basically draw tiny lines from this point to this point, a tiny line from this point to that point, and so on and so forth, which of course would allow us to compute a function value here. It would be this point, this value, right? No big deal, and again, this is really straightforward. There is not a lot of mathematics going on here. Straightforward. Still reasonably fast. And it's definitely much closer, say, to, in our case, didactic case, again, the original blue function. But it appears as if we could do better still. Right? So then the next sort of logical step would be to say, instead of using just lines, we could probably try to come up with higher order polynomials, right? Linear functions are polynomials of degree 1. What if we were to increase the degree of a polynomial that we would fit into the set of points? And we talked ever so briefly about Lagrange polynomials. What we do in this case is basically to sort of look at the overall situation, not just at two consecutive points, but looking at all of them. And if we are given, say, n such function values at certain discrete coordinates, we could apply a Lagrange polynomial of order n plus 1 in order to approximate this function. And again, mathematically, this is no big deal. You see, all you need to compute this interpolation f hat is really just the coordinates of those sample points, called xk here, and the function values at these sample points, called xi here. This is straightforward to implement. This, you don't have to worry about anything. If you turn this into program code and run it, what you'll get is this orange curve here. This is now, how many sample points do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be a polynomial of degree 11. And again, the important thing to note here that this polynomial has been created with respect to all the information we were given. And for certain ranges of the domain we are talking about, this is really close to, in our case, again, the didactic function we use to create the black point. However, because of this, 11 is already a fairly high order for a polynomial. High order of this polynomial towards the ends of the domain, towards the boundaries of the interval over which we are given sample points and function values, we observe this under and overshooting. Right. So, yeah, this is definitely not a bad idea, but certainly not a good idea either. In particular, this is again a very trivial example. We could be given, hundreds of points, and we would end up with extremely high degree polynomials, and that would certainly be a pain to compute, and it would suffer from severe over and undershooting at the boundaries of the domain. So then another idea could be to say, well, let's combine the best of two worlds. Let us stick with polynomial interpolation, but not with a kind of polynomial interpolation that considers all the information we are given at once, but let's try to come up with sort of piecewise polynomials. Here we had like, these are piecewise polynomials, right? Of order 1, degree 1, and we may apply the same idea, like sort of piecewise polynomials of a higher order. That is to say, we stitch together the interpolation function f hat from many different functions phi. Each of these phi I, phi 1, phi 2, all the way to phi n minus 1 are basically interesting to us only in a certain range that is only in between two correspondingly consecutive sample points. And we assume that each of these functions phi is a polynomial of degree 3. And accordingly, it would have 1, 2, 3, 4 parameters which we need to estimate, and we have n minus 1 such polynomials. So a lot of parameters for us to estimate. If we could succeed in doing this, for our example, we would end up with this. Right? Again, the orange curve is the interpolation I computed, and this is now really fairly close to the original blue function. It is, and I cannot stress this enough, different from the original blue function, but given the information available to us, among all the techniques we have discussed so far, this is probably the one that does the best job. It is basically possible to sort of get this original function back using just sort of finite polynomials. We could, instead of third order polynomials, go for higher orders, would become better, but would also entail more computational effort. So this is not perfect, right? But again, remember that for the situation we are actually dealing with, we don't even know the blue function. In the situation of image warping, all that we are given are these black dots. We have the pixel coordinates and we have intensity values at those coordinates. We don't even know the true blue function. Right? And in that sense, among all the orange curves we have seen, this one is the smoothest. So for our problem of interpolating images, it looks as if this one would do a satisfactory job. And here is another representation of that. So what we are trying to do is to come up with an interpolation function, this orange curve here, that is stitched together from certain, I don't know, polynomials phi, and again, like this curve, that it will continue somewhere down here, but it's not of interest to us. And it will continue somewhere here, but it's not of interest to us. We are only interested in the values of these polynomials in these certain intervals here. And this is indeed the curve that results from using cubic spline interpolation applied to these 4 sample points and their corresponding function values. So this looks fairly smooth. And then we discussed how to compute these parameters a, I, b, I, c, I, d, I, and I include this here because I promised you to do so, but I will not talk about it again. Right? This is not part of our recap, but what we did last time was we looked at this, and then here's something we didn't do last time. Okay, so I said in order, okay, order to solve for these 4 parameters, we may look at the different polynomials themselves, at their first derivative, at their second derivative, and that would provide us with a set of equations, but that's still not enough to solve for these parameters, so we would have to introduce certain additional smoothness requirements or constraints. Those are these. We discussed them last time, and here is an illustration as to why they are needed. The first 2 constraints on the previous slide prevent our solution from looking like that. Right, this is something we don't want to have. The third constraint on the previous slides prevents our solution from looking like this. This is okay, in a sense, you know, all of these are certainly interpolations of the discrete function I'm showing here. This one has the disadvantage that it does not even meet the sample points, the function values at the sample points, and then there are these discontinuities. Here, the function, the splines actually go through the discrete sample points, function values at the discrete sample point. And it's not discontinuous, but it's not really smooth. And we can prevent solutions like that from requiring this equation number 3. And then the last constraint, the one with the continuity of the second derivative, basically prevents solutions that look like on the right-hand side over there. This is, you know, this is definitely is a maybe acceptable solution, but still it could be smoother. Look at how this one looks like, and let's compare it again to what cubic splines actually would find this one here. Right, so we want to have something like this rather than like over there. Lots of algebra. Lots of algebra. Lots of algebra. Even more algebra, but you see that we end up with equations where the coefficients we want to determine are isolated on the left-hand side. Somewhere along the lines, you can check it at home, new variables did appear, but they have been defined such that we can compute with those. And again, even more algebra, and in the end, we end up with equations like these, n-1 equations like those, actually n-2, and we can rearrange the set of equations like these into, say, matrix vector form. And this is just to show you, you know, don't have to do that, but this definitely shows you that in order to solve for these things, because if we know these, like these m's here, if we know them, we can plug them in here and get all the coefficients we need for our splines. And this form of the equations just shows you, in order to get these things, we have to invert this matrix and multiply both sides of this equation with the inverse, and that can be done. And to us that looks daunting, but to your linear algebra packages this is nothing. Right? No problem at all. So, can be done. Why do we consider cubic splines in all of this? That is, why do we consider tiny polynomials of degree 3? Well, let us ever so briefly consider again a rather contrived example. Here is a function, I call it f of x, which is defined as minus x squared if x is less than 0, and x squared whenever x is larger or equal than 0. It's very easy for us to compute the first and second derivative of this function. So first of all, the function we are talking about is the green one here. This is minus x squared for everything that is less than 0, and x squared for everything that is larger than 0. Can easily compute the first derivative, that would be this function. And of course we can also compute the second derivative, which would be the blue function here. And you see that that is not continuous anymore. Right? Now the second derivative of this second order polynomial has a discontinuity at 0. But for our idea of getting a smooth interpolation, we required that the splines meet at certain points. We required that their first derivatives meet at certain points, and we required that their second derivatives meet at certain points. And we could not guarantee that the second derivatives meet at certain points. That is, we could not guarantee that the second derivative is continuous if we were, for instance, just to consider quadratic splines. So by looking at cubic splines, that is third order polynomials, we know that the second derivative still will not have jump discontinuities. That is the reason why we look into cubic splines. And I just said that. Okay, now on to something new. We have now seen a couple of ideas as to how to interpolate one-dimensional functions, or say functions of a single parameter. But the images we are talking about are, of course, two-dimensional functions, that is, functions defined over a plane rather than just over a line. So we have to think about interpolation of two-dimensional functions. And that is, we are given a discrete 2D function, say g, where for certain parameters ui and vi, we have certain function values, intensity values, say g at ui and vi. Right? And what we are looking for is an approximation, or interpolation I should have said, and I again will call it head, g head in our case, such that we can compute a reasonable function value at coordinates u and v that are situated in between those discrete coordinates we are given. What this image shows is a discrete function where I have singled out 4 discrete coordinates and the corresponding function values at these discrete coordinates. And we are now interested in computing a function value at this point. This is a coordinate in between the, let's say, a fancy term, lattice coordinate or grid coordinates of the discrete function we are given. How can we do that? Well, the first idea is to apply nearest neighbor interpolation, right? And this is a straightforward extension of what we discussed last time when we discussed nearest neighbor interpolation. And the only difference is that instead of looking for just one coordinate, or like sort of the only nearest neighbor coordinate, we have to determine 2 coordinates, x and y in this case. But it's so fairly straightforward that it does not even merit further discussion. The next idea is to extend the approach of linear interpolation to the two-dimensional case. And this is called bilinear interpolation. And again, this is an extremely straightforward extension of what we studied last time. And we can see this by breaking it down into 3 steps. Here is the first one. We are given 2 coordinates u and v that are situated in between the discrete grid or lattice coordinates of the function we are talking about. We want to compute a function value here. Well, one thing we could do is compute a linear interpolation, we know how to do that, between this function value and this one, and obtain a corresponding value at ui and v. The next the second thing we do is to compute a linear interpolation between these two values that we're given, and then be able to obtain a function value at ui plus 1 and v. Right. How would we continue? Exactly. Next thing we do is we fit a line in between here. There you go. And we can get a value at the coordinates u and v we are actually interested in. Would it have made a difference if we had done this first, then this, and then this? No. Right. So you shake your heads. No, it would not have made a difference. I want you to verify that at home. This will come back next time. And actually, next time we'll see the equation. Like these three steps can be, put into a single equation. Actually, no problem, right? Because think of it. Let me go back to here. Here we to here. Here we see the equation for one such line segment, right? This one. And instead of xi's, think of ui's and vi's. So you have this equation. You can compute this equation using ui's and vi's. Right? You can compute this equation, no problem. And you can compute this equation, which is basically three things that only depend on stuff you are given. You can plug them all together. And basically, I broke it down into three steps. But in practice, this is just one equation. It consists of three sub-equations, but you can put them all together. Right? We'll get back to that next time. But look at this and look into the fact that it doesn't matter whether we do this first and then that, or this first and then that. Okay, there you have. This is bilinear interpolation. There's nothing to be talked about here. That's all there is. That's all there is. Yeah, there is something we should probably, be aware of at this point. Let me go back to here. What if this was, I don't know, u0 and so this is basically the left boundary of the image, and this u would be here. How would we interpolate a function value at this point? If we do nearest neighbor interpolation at this point here, we can just look for the sort of closest coordinate and read the value from there. Right? For nearest neighbor interpolation, u and v do not have to be situated in between these four coordinates. It can be here, can be whatever. Right? For nearest neighbor interpolation, we can always find sort of the closest coordinate of all the pixels we are given. But for bilinear interpolation, if we end up at a coordinate somewhere out here, this funny trick with these three consecutive line segments wouldn't work. Because a coordinate out here, if this is the boundary of the, say, the left border of the image, coordinate out here, there is nothing surrounding that coordinate anymore. And this is what I wanted to say here, that by computing these inverse transformations, it may happen not only that we end up at real valued coordinates instead of discrete coordinates. So we may have to interpolate, and in general we have to interpolate, but it can be even worse in the sense that this inverse transformation leads us out of the domain over which the original image was defined. And if we want to apply bilinear interpolation in these cases, it cannot work. Because in order to do bilinear interpolation, we have to have four surrounding function values. If we do not have that, we cannot do this. We could use nearest there, there's no problem there. Right? So see, there's another advantage of this idea of nearest neighbor interpolation. But it may happen that this new image we want to compute cannot indeed be computed for every pixel. Right? And if you remember, we have seen a couple of warps already. In particular, we saw, I don't know, certain rotated images a while ago, and we saw this images represented in R and phi coordinates. There were lots of black areas in those images. Do you remember? And those black areas actually were black because I didn't know what color or intensity value to set there. Because I did apply a transformation that led out of the original image coordinates. Right, so, and how are we to represent the fact that something is undefined in terms of color values or intensity values? Right? I usually set them to black. This is a practical choice. Mathematically, it's really undefined. And practically, I replace this undefined by black. So this may happen. Be aware of that. Yeah. So we cannot guarantee that these pull warps will always end up at coordinates for which we can actually interpolate something. For the push warps we can, right? Because there we start with the coordinates that in the original which we were given. But as we saw, that may have sort of the opposite problem. Yeah, this is what I just said. And here is one more thing. So I've been talking about coordinates xi and ui and vj and whatever. And this is just for the sake of generality. However, the coordinates in an image are 0, 1, 2, 3, 4, 0, 1, 2, 3 for the rows and columns, right? So instead of ui and vi, I could just go as well for the index that counts them. 0 row, first row, second row, and so on and so forth. And the distance between any two such consecutive sample points in an image along the x and the y axis, of course, 1. Right. And that is all just to say that if we end up with a coordinate u that is situated in between two pixel coordinates I and I plus 1, and the coordinate v that is situated in between two rows j and j plus 1, we can easily determine the 4 surrounding coordinates of u and v just by flooring and sealing u and v. And I just, wanted to mention that. Okay, so, and now we turn our attention to the question as to how to extend this idea of cubic spline interpolation from the one-dimensional case to the two-dimensional case. And this is called bicubic spline interpolation. Does anybody already have an idea as to what will happen next? Who's taking courses in computer graphics? Did you discuss it there? Not yet? Did you? No? Okay. Well, then you actually learned something first here and can use it there. Let's see. Straightforward extension. Yeah, straightforward. Okay, it is exactly the same extension we just saw for the case of going from linear to bilinear. Now we're going from cubic to bicubic. However, to compute a spline, we need more function points than just like the two function values surrounding the coordinate unit. Right? So where for the bilinear case, we just focused on those 4 surrounding coordinates and the corresponding function values. For the bicubic spline interpolation, we look at a larger neighborhood, right? In particular, we look, and this is just, I don't know, I do it like this. I guess most software does it like this. But I don't know if this idea of a 4 by 4 neighborhood, so we have like the 4 closest coordinates in u and v direction. If everybody does it like this, I guess this is sort of the standard case, but other people may consider larger or smaller neighborhoods. But let's go for 4 by 4, right? So here's the situation we're given. We do want to compute a function value at this point here, situated somewhere in between these grid coordinates. And in order to do that, we consider the information in the 4 by 4 neighborhood about this coordinate. And then we simply fit splines along, say, the v direction at these 4 u coordinates. Once we have that, what is the next thing we could do? Or exactly, right? We can now compute the values here, 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 and here. And with these 4 values, we can compute another spline, this one. Once we have that one, we're done. All right? No problem. So this is how it's done. We don't have to discuss this any further. We don't have to discuss this any further. It's of course a bit more intensive in terms of what has to be computed than the other methods. But let us look at how these 3 methods do perform. First of all, see the black stuff here. Why is it there? Why is this warped image black at certain parts? You know, I didn't even show the original image. The original image is asterisks and obliques, and then I sort of rotated it a bit. And this rotation, if I apply pull warps for certain pixels here, I would have to look up an intensity value in the original image where there is none. Because if I compute the inverse transformation at this point, I end up at something outside of the original image. Don't know what to do in these cases, so I just go to black. This is why these warped images have these black areas at certain points. Does not have to be the case, but you know, in general, it may happen. Now, this looks fairly good. This is actually the image as it is. And in order to compute this one, I used nearest neighbor interpolation, right? As to our eyes, because of the resolution, this looks fairly okay. I have enlarged a certain part of this image, all right? And once again, this result here, I was given the original image, I computed a rotation, which is a very simple warp, you know, can do that. And the interpolation was done using the nearest neighbor technique. It looks okay, but if we look at the details, we see this. It looks rather blocky, all right? And let me go back once more. Lots of slides back. There we are. Blocky. Right? So the effect we can clearly understand from looking at the one-dimensional case, of course, sort of translates to the two-dimensional case. Right? This one looks blocky. We don't see it here, but if we look at the details, it's not so pleasant. Now, on the next slide, we'll see exactly the same situation, but I have applied linear interpolation. And I want you to focus on this image. Ready? Go. Nearest neighbor, linear. Nearest neighbor, linear. Nearest neighbor, linear. Do you see a difference? Nearest neighbor, linear. Nearest neighbor, linear. Here, you know, whatever. Maybe we don't see a lot of difference. They are there. And so in order to point them out, I have again enlarged a certain part of this image. So this was done using bilinear interpolation. It's not that blocky anymore. Right? It looks very good. What will be on the next slide? Exactly. I'll have the same result, same rotation, but now with bicubic spline interpolation. Focus on the image on the right. Bilinear, bicubic, bilinear, bicubic, bilinear, bicubic, bilinear, bicubic. Do you see a difference? It's much sharper. It's much sharper, right? So once again, this is the result we get from bicubic spline interpolation. It looks really good. I guess we can agree on that, right? This is the result we get from bilinear interpolation. It is blurred. If you think of it, you know, now mentally go back to the slides where I did the one-dimensional linear interpolation. This blurring comes from this, you know, sort of differences between the linear and the continuous function. And this is nearest neighbor interpolation. Okay. I have a stupid question now. Who's playing computer games? 3D games? Shooter games? I don't know. My question is stupid because, and this is, you know, goes also for your computer graphics people. Back in the day, when I used to play these games, Quake 3, I was really, like, you know, avid Quake 3 player. Graphics cards were not as powerful as they are today. You know, they became better at the end of the 1990s, but, you know, compared to where we are today, that was basically the Stone Ages. And as you know, for a pleasant gaming experience, you need lots of frames per second, right? The content of the virtual world has to be rendered as fast or quickly as possible so that it is smooth. And so back then, if you were playing those games on computers and your graphics card was not as powerful as the one for which the game was originally developed, the games provided you with the opportunity of changing the graphics settings. Do they still do that? I don't know, because I haven't played these kind of cases. And now you understand why, right? If they ask you for bicubic interpolation, this is what you get. If they allow you to go down to bilinear, then this is what you get, right? And this is okay, certainly, right? But it's not as visually pleasant as bicubic interpolation. But computing bilinear interpolation is tremendously faster than bicubic interpolation. Right? And for the games, the problem with interpolation is basically when they have to render textures. And we'll get back to that next time. But in playing these three-dimensional games situated in three-dimensional worlds, there's to be lots of three-dimensional graphics to be rendered, lots of textures to be mapped onto surfaces. And the question is, do you do that bilinearly? Right, then you'll get results like that. Or in terms of bicubic splines, then you'll get results like that. It looks better, but it's much more work to do for your computer. So now you understand your graphics card settings. Right? And in the end, it really does not make so much of a difference. But there you have it. Now we know everything about interpolation. There is not anything else we should discuss in this regard. And so therefore, let's finally, you know, do this. This is, again, there's no science here. Right? This is just, why would we ever want to do this? Because it's fun. It's fun. The cool thing is not actually to, you know, have this result, which is very cool in itself. The scientifically more interesting question is how to do this. This is the question we have to be able to answer as computer scientists. But not so much like what we can do with an image. There's like infinitely many possibilities, and depending on whatever situation you might find yourself in later on in life, you might have to do something like this. How can we do this? Let's talk about artistic image effects. Right? The first one is this fisheye or lens or magnifying glass effect. The idea is to warp an image such that the result looks like as if it was viewed through a magnifying glass. Say we would put a magnifying glass over here. Then that would probably be the result. Maybe I should actually bring a magnifying glass eventually and see. I don't know if I could put here, anyway. But you know, maybe you have seen it with your grandparents or whatever. When they have to read something, they have to have these, you know, huge magnifying glass, and you know, that's what you get. I'm not quite there yet, but you know, eventually it will hit me as well. I don't need those magnifying glass because I can compute all the documents myself. How do we do that? Here is the general idea. Now, what does it mean to magnify something? Right? To understand this, I have brought you a one-dimensional function. Let's call it g of u, and here's a warped function. And apparently, so the difference between the two functions over here, there is no difference. Right? This is the same as in this case here. Over here, the image is exactly the same as the original image. Something has changed at certain parts of the image only, where sort of, say, the center of the magnifying glass is here, and then, you know, in a certain surrounding about this center of the magnifying glass, everything will be enlarged, and everything else will remain unchanged. You can see this in this one-dimensional case where I assume that the center of the magnifying glass actually here, the 0 coordinate. This is the original function. In the warped function, something that is close to the center of the magnifying glass needs to be enlarged, and the stuff that is not so close to the center of the magnifying glass has to remain unchanged. Now, what does it mean to enlarge something? It basically means that for a coordinate, say, I guess this is pi, that is close to the center coordinate of the magnifying glass here in 1D, we have to compute the function value at a point that is closer to the center of the magnifying glass. So what we see here is a, I guess, cosine. Is it sine? Whatever. So some sine or cosine, I don't even know. And this is how it looked like originally. And here, in order to compute the value here, I actually looked up the function value here and set it here. And at this point, I looked up the function value here and set it there. So we see a stretching close to 0. And then we see some squeezing here. This is basically the same as we observe here. This is at the sort of boundaries of the magnifying glass. The stuff will be squeezed, where it's like sort of stretched here, it's squeezed here, but this is physically it's okay. So here we observe stretching of the original function. Here we see some squeezing, and then everything remains untouched. How do we do this mathematically? Well, for this one-dimensional case, we are given again the function g of x. We have to apply a certain transformation to the coordinates x. So we want to compute g at t of x, and that gives us the new function g tilde of x tilde. I don't use u's here because I don't know. And with respect to this problem of computing the fisheye or lens effect, this transformation t obviously has to have the following effect. This warp t has to have sort of large consequences if this shouldn't do anything at all. Let me rephrase this because okay. X is the distance from here to here, right? X is 0 here. If x is large, nothing should happen. You see that this function value was read from here, which is sort of exactly the corresponding function value there. So if this x is large, then the transformation should basically do hardly anything at all. However, for values x that are small, that is to say sort of close to the center of the magnifying glass, this has to produce a value that is less than x. Because, once more, I should have. Here is a small value of x, and the transformation actually produces an even smaller value of x. Right? And then we read the function from here. So this x coordinate is mapped to another x coordinate, and we read the function value from there. All right, and here is what that means mathematically. If we look at the identity function, it's the blue curve where we would map every x to itself. So 5 goes to 5, 10 goes to 10, and so on and so forth. We need a function that has the property that for small values of x, it produces something less than x. That is to say that the orange curve should be below the identity function if x is rather small, and it should approach the identity function if x is rather large. Can this be done? Of course it can. Right? And here is one of these functions that does it. So 1 minus e raised to the minus x squared divided by some number, doesn't even matter, produces curves that look like this. This is something that is less than 1 for a couple of numbers, and then becomes basically undistinguishable from 1 for larger values. Right? And if we multiply this function with x, we get exactly the orange curve there. So this is what I did to produce this picture here. The orange curve here is basically x times that function. So that can be done, there is no problem there. In other words, given what we just discussed, either we add something to the value x, to the coordinate x, that is negative if x is small, and is 0 if x is large, because if we add something negative to something small, it becomes even smaller. If we add 0 to something, it remains untouched. Or we multiply something to x that is less than 1 if x is small, and becomes 1 if x is large. Right? And the previous slide, what I used was this idea of multiplication. And that is to say we have basically two choices for computing these fisheye or lens warps. We can think of this transformation in terms of adding some delta plus, which has to be negative for small x and 0 for larger x, or we multiply some delta dot, which has to be less than 1 for small x, or larger than equal to 1 for larger x. Right? We already discussed this idea here, delta dot 1 minus e to the minus x squared over 2 sigma squared, like some numbers, it really doesn't matter. I like this one because so if we multiply x with delta dot, we can insert the definition of delta dot here, then multiply it out, and look and lo and behold, it's actually in this case it's the same. We can understand this as sort of multiplicative lens or additive lens. It doesn't matter. This is just fun. I just like to show that to you. It's not really important. What's probably more interesting is this slide here. Again, instead of thinking about how to design functions delta plus that meet these requirements, we can actually always do it like this. One could also say, well, let's define the extent of the warping region, the extent sort of the lens, and call it sigma in this case. This sigma is a different sigma than the one before, and I don't know, define the warp in a case-based manner. That is, if we are talking about a coordinate that is less than some maximum extent. We do something, and if it exceeds this, we don't do anything. All right? And blah blah. Okay, this is how we compute this. Okay. Yeah, let's okay. How do we compute these things? Once we have decided for a function t, now we can localize the lens. We choose a center mu, center point of this lens, and then we apply a pull warp. That is, we iterate over all the pixels in the new image. For each of these pixels, this is what you will find in the literature. They go to polar coordinates. They compute the angle phi and radius r of the current xy coordinate in the new image with respect to the center of the lens. So we go from Euclidean coordinates to polar coordinates. And then something is done to the radius value. This is sort of what we discussed for the one-dimensional case. Once the radius has been warped, they go back to Euclidean coordinates and interpolate and read the value from there. And yeah, you should have switched it. How to choose these warp functions? There are so many possibilities. Oh, I know why I didn't switch it. Because look that. See that I have defined these warp functions with respect to this value r. I'm way ahead of myself. Again, sorry about that. So let's okay. We'll forget about all of this in a second from now. But so far, why do I do? We have understood or talked about. Let me go back to here. Sort of one-dimensional warping. And if we discuss the distance or radius r, then this is a one-dimensional problem, right? So this is why for these examples here, I am considering warp functions with respect to the radius, that is, or the distance of a certain pixel to a center point. And the center point for all these things was, I guess, somewhere here. And what I'm trying to hit home here is that this is not science, right? How do you do this? How to choose these you know, it's really, there's whatever, you choose them, right? As long as they have those properties we just discussed, they will do the job. But whether you want to have, like, you know, really spherical distortions or rather smooth one, or exponential ones, or in a sense linear ones or quadratic ones, right? In these examples, all these images are 400 by 400 pixels. The center point is somewhere here in the center, and the maximum extension, this is done in a case-based manner, was set to 150. Here are different functions that do the trick. There you have it. Right. I cannot tell you what to do here. If you ever have to do this for yourself, you have to think about a suitable function that has the properties we just discussed. And as you can see, there are many. Now, and here is what I actually wanted to tell you. I haven't checked any textbook lately, but usually if I, or last time I read about computing these fisheye warps, I always find that they do it like in terms of polar coordinates, right? So they iterate over the new image. For every xy coordinate in the new image, they compute the polar coordinates with respect to the center of the magnifying glass, then warp the radius, and so on and so forth. It is much smarter, and we'll see why next time, to think about the warp function t as something like a central force, right? And that is to say that instead of going to polar coordinates, we may just as well compute, given like a pixel coordinate x, compute warp functions t of r and x, where r is simply the vector pointing from the current coordinate x to the center mu of this magnifying glass, and take it from there, which is to say instead of breaking down an inherently two-dimensional problem, the problem of warping a two-dimensional image, translating it to a one-dimensional problem, warping the distance to some center, we can do it in 2D right away. Right? We just have to consider warp functions with respect to vectors. And really, I mean, that can be done, right? I am not specifying them here, but now this is a vector. This is something that points from x to mu towards the center of the magnifying glass. And how to define these functions delta plus, you see, you know, do whatever you want to. You may want to compute the magnitude of this vector and then do something to the magnitude of this vector, but the thing I try to hit home here is that we do not have to do this in polar coordinates. We just don't. We can do it with vectors right away. And here is an example. Right? Again, this is a vector, but if we square it, it becomes a number. And this is basically one of these exponential warps we just saw earlier. No polar coordinates necessary whatsoever. So don't believe the stupid textbooks or web pages you find out there. They are stupid. They really are. They really are. So years and years ago, when I first prepared this lecture for the first time ever, and I tried to read up like how is this being done. I read it in books and on they weren't called blogs back then, but you know. And I never understood why they did it in such a complicated. Why go to polar coordinates first? We can think of this as a vector warp. Right? We have something, we are at a certain coordinate, we know where the center is. There is something that points from where we are to move into this direction, you know, with a certain speed if you want, and we're good. And next time I'll show you why this is a much smarter way of doing it. So don't believe the stupid books and web pages out there. Okay, ever so briefly, because we are running out of time. I don't even know why. Here is another effect. Waves effect. Now, what are we trying to accomplish here? The idea is to transform or warp the image such that the result looks like, for instance, as if it was a picture on the bottom of a swimming pool and you just, you know, had thrown a stone into the pool and the water ripples and there are waves, and because of the waves the image on the bottom of the pool becomes distorted. So this is actually what we see here, right? Depending on the weight of the stone, you might get something like that or something like that. So the physical analogy here is rather loose, as with the fisheye, but no problem. So how do we do this? How can we compute images like that? Well, again, we have to consider a certain warp function. The fact that it's supposed to be a wave strongly hints at the idea of using sine or cosine. I'm using sine. And let's just define this warp function to be x plus alpha times sine of nu times x minus phi. And the good thing of having discussed Fourier transforms first is that this should not shock you anymore. Right? We know about amplitude frequencies and phases. And we recognize this as a wave function. This is basically all I have to say here. Is just an illustration of the effects of these three parameters. So we have parameter for amplitude, frequency, and phase. And by changing the frequency, this is again the identity function. Here we add sine to it. You see that at some points we have something that is larger the identity, at some points we have something that is less the identity. So this gives this stretching and squeezing effect, right? And well, if we change the frequency of this function, we may have, you know, less pronounced stretching and squeezing. If we change the amplitude, You know, stretching and squeezing may be even larger, and faces and so on. This is just illustrating the effect of these parameters. And again, I want to hit home. We don't have to do this with polar coordinates, even though you might read that. We can right away do this in terms of vectors. Right? Again, there is a certain center of where the stone has sort of hit the surface of the water and begins to sink. There's the center of the wave, like where the stone hits the wave will be propagating from there. So we have a center, we have a vector r, just as in the previous case, that defines the direction from the pixel we are currently considering to the center of the distortion. And then we basically have to apply a sine wave to the distance between the pixel x and the center, which is the norm of r. Multiply that with the frequency, subtract some phase, multiply some amplitude, add that all to x, and then everything has to be, of course, moved into the direction towards the center when we use this unit vector here. Right. So we can do this using vectors directly. There is no need for us of having to compute polar coordinates. So basically this delta plus thing, which was a rather simple function just a couple of slides ago, now depends on several parameters. But you know, we add something to it. Again, this is exactly the same idea. We have a walk function that adds something that may be larger or less than the current value, but we just add something. And here is the idea of a swirl effect. So these images, I don't know, imagine you would have cooked the pudding, and then you have drawn an image on the pudding, and then you insert an immersion blender, and this is what you get, right? So again, we can also simulate physical effects like that. So I would have inserted an insertion blender here, and immersion blender there, and this is what you get. How do we do this? Again, whatever. This is, it becomes repetitive. What can I do? At some point, there is a center point of the distortion. This is where we insert, sort of like metaphorically, where we insert the insertion blender, immersion blender into the image, and then we switch it on, have it rotate for a couple of rotations. Or here, obviously it was not such a powerful one, but had a larger sort of radius. So again, we assume that there is a center point, let's call it mu, and we consider a certain pixel coordinate x, this is certain, which provides us with a certain radius vector, something that points from x to the center. And now we want to do a displacement not along the direction from where we are towards the center, but sort of orthogonal to that. Does not have to be orthogonal, but for instance, right, we are interested in a walk function delta that is not along the direction from where we are right now towards the center, but sort of perpendicular to that. Does not have to be perpendicular. Yeah, again, look at this. So if people go to polar coordinates, this is what they do, right? They compute this vector anyway, and then they take the norm. Here they use polar coordinates because they're not just interested in this radius magnitude r, but also in the angle phi. And when we talked about complex numbers, we already met these two quantities here. So this is arctan. Can do this. Once we have computed this phi here, we this time would have to walk the phi. Right? Not the radius, but the angle. Again, like this is, you know, how, this should be a phi, I don't know, my mistake. Again, how you choose these functions that do something with this angle is to your liking. Really, nobody cares. The important thing is that if you want to swirl something, the warp has not to happen along the direction towards the center of the warp, but so perpendicular, or at least not along the direction towards the center. Instead, and I'm hitting it home, of going to polar coordinates. Again, we can do this directly in terms of two-dimensional vectors and Euclidean coordinates. Right? And I'm just writing it like this. This is, let me see, I have a picture here. There it is. So what we are actually dealing with here is the following situation. Somewhere there is the center of where we insert the immersion blender into the image. And a certain pixel in the image is at a distance r with an angle phi, say, with respect to the horizontal axis. And we would have to compute a vector delta that moves this x away from its current location. It's supposed to happen in an angular fashion. Right? Note that in this sketch, this vector delta is indeed not orthogonal to x, or it's something else. But this is the basic principle here. This is what should happen when you want to compute a swirl effect. You would have to sort of rotate the pixel coordinates away from where they are right now. And looking at this picture, look at this. So we have a vector x and a vector u. We can sort of compute that vector u from adding delta to x. And this would allow us to solve for delta. And at the same time, we could express this vector x in terms of r phi and the corresponding sine and cosine functions. And we could also express u in terms of phi prime and r and the corresponding sine and cosine functions. So here are a couple of equations for how we could represent u and v, x and y. And if we were to use those here and would plug them into this definition of delta, we get this, right? And the only reason I am doing this is again to show you that we can understand this as a vector transformation. There is no need for us to first go to polar coordinates, then warp the phi value, and then go back to Euclidean coordinates. We can do this right away, like so. Yeah, that was all for today. So, today we have learned about, and this is by far the more important thing, two-dimensional interpolation. We saw that these ideas of nearest neighbor interpolation, linear interpolation, and cubic spline interpolation can be extended from the one-dimensional case we studied in detail last time to the two-dimensional case that is actually of interest to us in the area of image warping in a very natural and seamless manner. Right? And we talked about two-dimensional nearest neighbor interpolation, which is so trivial that I really did not actually talk about it, but this is really straightforward. We talked about bilinear interpolation and bicubic interpolation. And we saw what kind of results they produce. And we saw that actually all of them, with respect to the images that were on the left-hand side, it looks okay. The details vary dramatically. And it appears that nearest neighbor interpolation is by far the fastest thing we can do. And bicubic spline interpolation, among the methods we have discussed, and there are of course many more interpolation methods, is the slowest, but gave sort of the most pleasant results, and in a sense bilinear interpolation is somewhere in between those two. Right? But you now understand how they work and can therefore appreciate if, say, your game allows you to change the graphic settings from bicubic to bilinear or whatever, you know why the game would offer that possibility now. Because bicubic spline interpolation requires a lot of computations and therefore decreases your frame rate. And then we talked about artistic image warping, which I, look down upon because, but I shouldn't. So I have to excuse myself for, hand waving these things away. Like scientifically, there's nothing to it. This has nothing to do with science. Seriously, this is really just fun, and this is the reason why I sort of, discussed it in this manner. But now that I'm summarizing this, I realize I should not have done it, because this is actually probably the coolest part of all our lecture on image processing, because looking at these things, then I really should not have made fun about it. There's no science here, but the great thing about it is that image warping visualizes mathematics, right? You have, I don't know, arguably complex mathematical expressions like this. You turn them into computer code, you hit return, and you see what it does. This is actually one of the really pleasant aspects of a lecture on image processing. We can see mathematics in action. Literally, we see what the equations do. And the reason why I am sort of, frowning upon this part of the lecture is because, it is so arbitrary. It is so arbitrary. Like, how to choose this? I cannot really tell you. You may use whatever you want to. And by far the more important aspect we discussed today is captured in this picture here. When we talk about image warping, we have to, or may probably understand it as doing something to the identity mapping. And in the case of the fisheye lens, we want to come up with a function that for small values is less than the identity. We're talking about multiplicative warps, and is exactly the identity for larger values. If you understand this picture for what it says, then all of this here is really, then you can comfortably, choose whatever kind of functions would produce these effects. And that is not just for the fisheye, but also for the wave select. Why would I actually choose a sine function here? It is arbitrary as long as it has the effect that for certain values we get something that is larger the identity, and for certain other values we get something that is less the identity, then it will produce such a wave effect. For the swirl effect, this is not so easy to be visualized, but this is basically captured in this picture. As long as there is a way for us to compute these displacement vectors delta, not along the direction from x to the center of the force mu, as long we can come up with a function such as this one here, this is something that produces this delta, we are good. Right? And because all of this is so arbitrary, I'm making fun of it. I should not, because these things really allow you to see mathematics in action. So I'm sorry about this, and next time actually we'll see even more artistic image warps, and I might actually even make more fun about it, but please excuse me. This is everything for today. Are there any questions? Yeah.
Yeah. The second thing, the second wave effect, you say we should use 10 because we are transforming in Fourier and it's easier for us.
No, 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 no. I did not say that.
I'm sorry. Maybe
No.
this is wrong.
No. Oh boy. No. I did not say that. I said. So his question was, we should use the Fourier. No, not at all. No. What I said is that the good thing about us having discussed Fourier transformations is that even though I emphasized the notion of amplitude, frequency, phase, and wave here, there would have been no need for me to do this because you're already familiar with these things. But if no. This has nothing to do with Fourier transformations whatsoever. Right? So not at all.
Yeah, because in the beginning you talk about functions, and I thought that we have to change to the frequency domain or something.
No. Because, okay. No. Almost there. Oh, here we go. What is different about the kind of transformations we are studying right now compared to the Fourier transforms and to the filtering operations we have studied so far is when we look at Fourier transforms, we take these functions and represent them in a totally different space. Right? Very difficult for us to visualize that space. Can be done. And then we may do something to the functions over here and map them back. But when we apply these filters, and whether we do that in the frequency domain or in the space domain, what we basically do is something to the intensity values. When we are talking about image warping, we transform the coordinates, not the intensity values. This is a very, very crucial difference. All right.
Thank you for sharing.
Yeah. Any other questions? Yeah.
One question is, all the affine transformations that we do, are these all what functions?
Yes. Yeah.
And another question,
Yeah.
on the first transform, on the first artistic effect that
Yeah.
we've done, for the fish, I think we have a magnifying part
Yeah.
and a part that is getting shrinked.
Yeah.
So how do we depict that on the graph, the shrinking part of that?
Oh, it happens automatically. You don't have to worry about
And
this.
on the graph, how do we see it on that graph?
Okay. So here the difference is rather large, right? And then it becomes smaller here. And let me go back to this one. So basically here you have to think of it like the difference between this point and this one is rather large, but the difference between this point and this one is rather small. Right? So and this is because or this is what leads to the squeezing here. That while the difference between this coordinate here and this one here is rather large, the difference here is rather small. And where is it? Okay. So you know, for 0, typically 0 is a strange number to work with. So if we multiply something to the number of x, but here we have large differences, and they become small here. And because the differences are large here, we see really pronounced change in the function. And well, mathematically, it really just so happens that while this is being stretched, this has to be squeezed in order for this transformation to work at all. And we can see it in this image because, look, here stuff is being stretched, whereas here this is squeezed. There's actually nothing we can do about this. This happens automatically because so it has to happen, right? So these differences, they become ever smaller, and then eventually vanish. That is, here there is no difference between this coordinate and this coordinate. And so there is a certain transition region where we observe this squeezing. So it happens. Nothing we can do about it. We don't have to choose it. And it typically happens with respect to the fissure, as I'll show you later. Sort of the R max is somewhere here, say in this example. R max would be here, so there's a huge effect close to the center, and then these squeezing effects close to the boundary of the fissure. Let's have a look, and then we are good. Yeah, this one is very dramatic here. Right? So here you see that along the boundary there's something else entirely than here. So here's magnification. Here's sort of this is squeezing. These things are squeezed. It happens automatically. Any other question? Great. Then see you on Thursday.